We just looked at the area problem, which is basically the problem of how do we find the area underneath a curve for a certain interval. And we're now going to look at a related problem. Might not seem to be related at first, but it very much is. It's called the distance problem. And both of these are going to be applications of integrals, which is what we're going to see very soon in this class. But for now, I want to talk about the distance problem. Now, the distance problem is the problem of finding the distance traveled by an object during a certain time period if we know the velocity. So suppose we know the velocity and we want to figure out the distance. Now, it turns out this is a very easy problem if the velocity is constant. We have a formula for this. Distance equals velocity times time if the velocity is equal to a constant. But that's no fun. We want to look at what happens when we have velocity that varies. And so this becomes a slightly more difficult problem. And the way I want to frame this to you is by giving you a supposition. So let's suppose the odometer in a car, which tells us how far we've traveled, is broken, and we want to estimate the distance driven over a 30-second time interval. Now, I know that usually we measure things in miles and miles per hour, and in 30 seconds, you're not going to get that many miles. But let's pretend that our car works with feet per second, which is just a more reasonable unit here. And let's pretend that we have a speedometer that tells us how fast we're going, and we take readings every 5 seconds in that 30-second period. So let me show you what those readings are. Now, here is a chart with all that information. When we first start measuring in that 30-second interval at the very beginning, it's 25 feet per second. Then after 5 seconds, it's 31 feet per second. 5 more seconds later, 35 feet per second. The next 5-second interval, 43, then 47, 46, 41. So we know that our velocity is changing, but we don't know what it is as a function, and we don't know what it is every moment. We just have this handful of values every 5 seconds. Now, what we can do is we can make estimates very similarly to in the area problem when we were estimating the area in one of those strips by using a rectangle. So here, if we look at the interval from 0 to 5 seconds, we know that's a 5-second interval, we could just take either 25 or 31 as the velocity and say, well, let's estimate and just say that that was the velocity for the whole interval. We could pick either. It's kind of like picking left-handed rectangles and right-handed rectangles if we're picking the beginning of the interval or the end of the interval. So let's do left-handed approximations, for example. So we know that distance is velocity times time. And so for this first interval, the velocity, if we're doing kind of the starting velocities or the left-handed velocities, is 25 times the time is 5 seconds. And then plus in the next interval, from 5 to 10 seconds, we take that starting velocity. So the velocity is 31 times, again, the time is 5 seconds. And then we keep doing that for the rest of the intervals. The next interval is going to be 35, then 43, then 47, and then 46. So we've got 35 times 5 plus 43 times 5 plus 47 times 5 plus 46 times 5. Each one of these is taking distance equals velocity times time for each of these little 5-second intervals by assuming that the velocity is the velocity at the beginning of that interval. So these top 6 are the ones at the beginning of each of those 5-second subintervals. We could even recognize that each of these has a 5 in it, and so we could pull out the 5, similarly to how we pulled out the width of each of those rectangles in the area problem. And so it's 5 times 25 plus 31 plus 35 plus 43 plus 47 plus 46. And when we do all of that math, we get 1,135. And because this is a distance and we're measuring distance in feet here, we have 1,135 feet using the left ends of each of those intervals, the left end points. We could also use the right end points of each of those intervals. I'm going to skip the first bit and just move to the point where we recognize that the time for each of the intervals is 5, and so we just have to write in the velocities. Now, before we used the left-handed velocities, the left-handed intervals, so that would be these ones. But if we're doing the right-handed ones, it's going to be these ones, because if we look at this interval, the end time is here, and this one, the end time is here, etc., all the way down to the bottom where the end time is here. So always we're including all of the middle numbers, but if it's a left interval, we're including the one on the far left, or the one with the smallest x value, and if it's right, we're including that final one. So in this case, we've got 31 plus 35 plus 43 plus 47 plus 46 plus 41. And when you go through and do all of that arithmetic, you get 1,215 feet. And so the estimates that we get for the two different possibilities are 1,135 feet and 1,215 feet. Now, we don't know which one is closer. We also don't know if in one of these intervals it sped up really quickly and ended up even faster than 47 feet per second, because we don't have the graph. We don't know if, what's an underestimate, what's an overestimate. We know nothing about what happened in between these time periods that we're looking at. So it could be greater than 1,215 feet, could be less than 1,135 feet. We're not really sure. This gives us an estimate. But we will see later that if we have all of the velocity information as a function of time, not as just a handful of readings, but if we know the velocity as a function of time, we're going to be able to use antiderivatives and eventually integrals to figure out what that exact total distance is.